Imagine this. Everything you know about the world, books, photos, passports, movies, messages, maps, music, science, money, government records, even your own memories in digital form, all of it depends on one thing: storage. Not the internet. Not apps. Not screens. Storage. Because before information can be shared, copied, searched, streamed, or protected, it must be stored somewhere first. And this is what makes the history of data storage so amazing. In just a few generations, humans went from shelves full of paper books to machines that store terabytes of data in glass for potentially more than 10,000 years. Think about that. We started with libraries. Then came giant computers that filled rooms. Then punched cards, magnetic tape, hard drives, floppy disks, CDs, DVDs, Blu-ray, flash drives, memory cards, cloud servers, and now experimental storage in glass. This is not just a story about machines. It is a story about memory. It is a story about how civilization tries to protect knowledge from time. So today, we are going on a full journey through the evolution of information storage. From the first room-sized digital media, to the devices in your pocket, and finally to the strange storage of the future. Before computers, the best way to store knowledge was the book. For a very long time, books were the most important information technology on Earth. A book does not need electricity. It does not need software updates. It does not need Wi-Fi. You can open it after 50 years, and if it was protected well, it still works. That is why libraries became one of the most powerful tools of civilization. They allowed ideas to survive their authors. They allowed knowledge to travel between centuries. Today, huge libraries still hold an unbelievable amount of material. The Library of Congress alone has enormous collections that no single person could read in one lifetime. But books also have limits. They take space. They are heavy. They require paper, ink, transport, shelves, and climate control. As the world became more industrial and more technological, people needed new ways to store information. They needed storage that was smaller, cheaper, faster, and most importantly, machine-readable. That is where the digital age begins. When people think about storage today, they think about flash drives, SSDs, cloud accounts, or memory cards. But the first digital storage systems were enormous. Some of them were as large as furniture. Some were part of systems that filled an entire room. One of the earliest important storage technologies was magnetic tape. The UNIVAC I used the Uniservo tape drive, one of the first tape storage systems for a commercial computer. These tape units were large, separate machines, and they looked nothing like the small devices we use now. Another early form of storage was the magnetic drum. It was a rotating metal cylinder covered with magnetic material. As it spun, the computer could read and write data on its surface. By modern standards, these systems were slow, noisy, huge, and limited. But at the time, they were revolutionary. For the first time, machines could store and retrieve digital information in a practical way. This is important to remember. Digital storage did not start small. It started heavy, mechanical, and expensive. After that came one of the most famous early storage media, punched cards. A punched card was simple. It was a stiff paper card with holes in specific positions. The pattern of holes represented information. In a strange way, this was one of the most physical forms of digital storage ever created. You could literally hold your data in your hand. A program was not invisible. It was a stack of cards. This system may look primitive now, but the idea behind it was powerful. The machine was reading two states, whole or no whole. Presence or absence. That basic idea is still with us today. Modern storage may use electric charge, magnetism, or laser-written structures, but at the deepest level, it still comes down to binary states, 1 and 0. That is one of the most fascinating things in this whole story. The physical forms changed completely. But the binary logic stayed. Tape became very important because it was practical. It was cheaper than many alternatives. It was removable. It could be stored offline. And it made it possible to move data between machines. This was a major step forward. Data was no longer trapped inside one computer. It could be recorded, removed, archived, and moved somewhere else. That simple idea created huge possibilities. Governments could store records. Companies could back up data. Researchers could save results. Organizations could preserve large amounts of information without keeping everything in active memory. Even today, tape has not completely disappeared. It still survives in some archival environments because it can still make economic sense for long-term storage. That shows an important rule in technology: old systems do not always die. Sometimes they just become specialized. Then came one of the biggest breakthroughs in storage history, the hard drive. In 1956, IBM introduced the 305 RAMAC, which included the IBM 350 disk file, widely recognized as the first commercial hard disk drive. It used 50 large platters and stored about 5 megabytes of data. Today that sounds tiny. A single photo from a phone can be larger than that. But at the time, it was a huge achievement. The real breakthrough was not just capacity. It was random access. Tape is sequential. You move through it in order. A disk lets you go more directly to the data you need. That changed computing. It made storage more flexible and more useful for real work. Hard drives store data by magnetizing tiny areas on a spinning surface. Some areas represent one state. Others represent another. That is how files, programs, and systems are stored. This principle remained central for decades. Hard drives became the main storage system for personal computers, business machines, and servers around the world. Then came the floppy disk. For many people, this was the first time digital storage became personal. You could save your own files and physically carry them. Homework. Games. Office documents. Software. Photos. Code. The floppy disk was not powerful, and it was not very reliable by modern standards. But it changed behavior. It taught millions of people that data could be portable. That was a huge cultural shift. People no longer expected information to stay inside one machine. They expected to take it with them. Not simple at all. If you want to see storage engineering at its most extreme, look at the flight recorder, often called the black box. Its job is simple: keep critical data safe, even during a crash. Older systems used magnetic wire or tape-like methods. They worked, but recovery could be difficult. If the medium was twisted or damaged, engineers had a hard time restoring the recorded information. Modern black boxes use digital memory. Often, they use protected memory modules inside armored containers. The system is built to survive heat, shock, vibration, impact, and other extreme conditions. This is a very different kind of storage design. It is not mainly about speed or low cost. It is about survival. That is an important lesson. There is no perfect storage for every purpose. Different missions need different solutions. A phone needs convenience. A server needs capacity and speed. An aircraft recorder needs extreme protection. This is one of the strangest things about modern life. People carry advanced information carriers every day and almost never think about them. Bank cards. Travel cards. ID documents. SIM cards. Phones. Smart devices. Inside many of these objects is a microchip. These chips are tiny, but making them is extremely difficult. They are built in clean rooms. Dust is a serious problem. The process includes light, chemicals, etching, metal layers, and repeated microscopic patterning. At this scale, manufacturing becomes almost unbelievable. What looks like a simple card or ticket may contain a highly advanced product of microelectronics. This reminds us of something important: digital information always has a physical body. It may be hidden, but it is never magic. This is one of the strangest things about modern life: people carry advanced information carriers every day and almost never think about them. Bank cards, travel cards, ID documents, SIM cards, phones, smart devices. Inside many of these objects is a microchip. These chips are tiny, but making them is extremely difficult. They are built in clean rooms. Dust is a serious problem. The process includes light, chemicals, etching, metal layers, and repeated microscopic patterning. At this scale, manufacturing becomes almost unbelievable. What looks like a simple card or ticket may contain a highly advanced product of microelectronics. This reminds us of something important: digital information always has a physical body. It may be hidden, but it is never magic. Now we come to one of the most amazing modern developments: glass storage. Microsoft's Project Silica is working on storing data inside glass using lasers. Microsoft. According to Microsoft and research published in Nature, this kind of storage could preserve information for more than 10,000 years under normal conditions. Nature +1. That is an astonishing number. Not 10 years. Not 100 years. 10,000. The method uses laser pulses to create tiny structures inside the glass itself. These structures can later be read and decoded. This is important because glass can be very stable. It is not affected by magnetic fields like a hard drive. It can survive conditions that would destroy many ordinary storage devices. This does not mean glass will replace your phone storage or your laptop SSD. That is not the point. This is about archival storage. It is for information that must survive a very long time. Historical records, cultural archives, scientific data. Large collections that institutions want to preserve far into the future. In a way, this idea brings us back to libraries. Only now, instead of shelves of paper, we may one day have durable glass archives that protect knowledge for millennia.